Right, we're the tethered aortic robotic roller.
Yes.
We call it STARC. Make it easier to remember. Yes, I'm Tom Kalisky, and my group is Tor Anderson, Neeraj Majit, and Neeraj Dhole and Ramzi Majit. Sorry. And our mentor is Eliah Arnoff-Spencer. And so,
Yes, you did.
yeah. Alright, this is just a small thing to get your eye.
Ears.
So the motivation for our project is typically a lot of surgeries that require basically inserting some stint or any other thing to your body. Usually very invasive, very costly, very risky to the patient. We're trying to design a new approach, basically something that's minimally invasive and doesn't take a lot of training and can be used in very different settings and not just, I guess, developing countries. Our hypothesis is just we're very limited. We try to limit ourselves to something, just a small aspect of that problem. So we try to test if a soft actuated robotic crawler is capable of navigating through an aorta-like environment. And we decided to go with the inchworm design or concept, just to move inside a pipe, which you have with two anchors moving and one center actuator basically moving forward or backward. And hopefully against flow of blood or any other fluids. We tried a few designs. First thing was we called it a prongs anchor design, which was basically it's basically like a piston that's connected to prongs that, when actuated, is reaching out to the side walls of from all sides to grab to the walls of the aorta or the tubes or whatever we're testing, and in order to anchor. And we had some issues with that. We tried just 3D printing. We didn't try molding because it involved too much of like different materials, and we didn't. I guess we didn't have the time to deal with that. I think it's doable, but it just involves two small details. This is an example of what we were able to achieve, but it proved not to be reversible enough because the friction was too high when you try to reverse it. We tried to reverse it with rubber bands or with vacuum in the chamber. But that wasn't repeatable enough, so we decided to abandon this concept. Another concept that we tried was the same prongs or anchoring using SMAs. We had very, very thick SMAs. We're hoping they'll give us more force to anchor down against the flow, but that proved to be very hard to program and, I guess, actuate, or not actuate, I guess, shape it against actuation. Because when those actuate, they have a lot of force, but then you need basically a lot of force to move them back to the original state. And that proved to be hard, even just by brute force with I guess, pliers and everything. That was very hard, and they were very costly, so we couldn't try too many tests on them. Here's one test that we tried. But, okay. Yeah, so we had to abandon it for now because we didn't have enough time. Ramzi's gonna present what we currently went with.
Yeah, so if you've seen the video, this is our current design. And what it is it's pretty much silicone molded tubes, as you can see in the furthest image. And we added like an air chamber around the middle of the circumference, just so it will equally distribute the air throughout. Next, we added just like typical balloon material on the outside, and then sealed it up with just hot glue. We couldn't really look up materials that would adhere through all these different materials, so we just went with just hot glue. And what we did was we also included 2 rigid 3D printer rings on either ends, so you can still see it's flexible and soft, but it holds its shape very well. So the reason we added those was, one, to hold its shape, but also prevent the balloon from inflating inwards, since we want all the expansion to be radially outside. Next, for the middle linear motion, we used a typical McKibben actuator, which is just a balloon inside of an extendable sleeve. What we did to connect the anchors and the middle actuator was just leave some extra strands of the McKibben. We separated it into 3 different strands and then just shrink these different components. And there should be a piece somewhere around there with the McKibben, and you can pretty much just attach that to the anchor directly. And then the last thing we added was just the tube, which helped us control the robot pneumatically. Yeah, I think that's it. All right.
Ramzi talked about the design that we made. So I'll talk about how we controlled it. So all of us had a control board with us, so we included a control board. So what we did is we created a sequence or an open loop control sequence for a robot. So the sequence that you see here is based on empirical data. So we tried lots of variations, and this is what we got. So this sequence that you see here is actually optimized for the green robot that we made. And we also incorporated feedback control into our robot. So like we don't want these to pop. So we're controlling the pressure also. So if it goes above certain pressure, it cuts off the actuations. So here's a video of the robot moving with our fluid board. So we made the robot, and then the next plan was to test it. So first thing we did was to test it in a pipe. So that's our dry setup. So we just had a pipe that is an inch thick, and inserted the robot inside it, and just made it go throughout. And we controlled it using the fluidic board, also using manual pressure control. So we tried both things. And then we also created a test setup which had what we wanted it to be blood, but it's actually water, colored water. So we are just running water. So what you see here is a pump that's actually circulating the fluid from this reservoir. And over here, I'm not sure if you can see it, but the robot is over here. That's our robot. And we control the robot using the fluidic board. And I have video the robot working. So no fluid is actually flowing through it right now, so the pump is off. And you can see the robot moving up the side. And now the fluid flow was turned on. I don't know if you guys got a chance to see it. Don't blink. Yeah. But it just flows with the flow. Do you see it?
So it's hard to see. Does the robot get carried by the flow,
Yeah,
or it
yes.
stays?
Yeah.
Oh, okay.
It doesn't stay though.
Okay.
Okay, and Tom, talk about
Yeah, so one thing I forgot to mention about our final design is we use tubes and rings. The whole idea is to allow flow through the center of the robot. But if you look at them, you can kind of see it's pretty blocked. But given more time and iterations, we probably can affect fabrication. So I mean, we talked about different colors of these robots, and what they pretty much mean are just a different total crawler length. And so we wanted to test just a parameter given the time we had left of the design to see how it changes performance. So we thought it was easy to just kind of test the crawler length. So the orange one was 26 centimeters, the red one was 16.5, and the green one was 12.9. So we kept the anchors constant, give or take some fabrication issues. So the main thing we were changing was the McKibben length. So as you can see in these plots, the red bar is the total McKibben length, and then the blue bar is the decrease in length as you actuate it. And they're all around, so the orange one was about 16%, red one was 15% change in length, and green was 13%. So we thought this was fairly consistent in our fabrication process. Just do some ATCC. But the idea behind this is you can see that longer McKibben length has a greater linear motion, but it also introduces challenges like if you have a long, slender segment, there's more chance that it might buckle or deflect in the wrong axis. And so this was something we wanted to test out and see how it changes the performance of our actuators.
So then one of the things that we wanted to also test out or achieve is basically when something will be completely automatic or something it doesn't require training to actuate or to work with. So we want to see if our control board actuation is as good as manually controlled. So we tested out the same actuator using two different control methods. One of them is manually by hand actuating each actuator, each segment, and then one of them using the control board. And during this short test, we can see that the dotted line is the manual one, which shows that actually the manual control was moving faster, but it's not as consistent or not as linear. So we think that over time the control board control or motion is much more reliable, and we can say that over longer periods of time it's probably going to be faster as well, because the person controlling it needs to learn and also gets tired and gets distracted. So this proves that we've still got a lot to work on our control code, I guess, or our control program, but it's definitely would be, I wouldn't say it's better, but I would say it's just as good over longer periods of time. And then those are the different speeds that we achieved with the different lengths of the McKibbens, or the different actuators. So that pretty much consists with what we assume, that the longer the actuator is, the faster we can move, since the cycle time is the same for all of them for what we tested, and every actuation cycle is going to be longer with a longer McKibben. But in here we only focus on the speed. We don't focus on the buckling or any other distraction that the longer actuator might cause, especially when you move inside of fluid or against flow, which might give you less push force. We didn't test that yet, but as far as just speed of actuation, we see that the longer the better, or the longer the faster, I guess.
Yeah, so just to recap, the objectives that we did complete were moving within a dry and wet tube environment. And so the design trends, which Tom already sort of hit on, were the main takeaway is that a longer McKibben length, the center segment, means that we can move it faster. But the trade-off there is that you're a little flimsier in sort of like the horizontal direction. And so that's a trade-off to look at. Yeah, and so there is a potential advantage for the crawl or the prong design that we had that we showed early on. There was a prototype being passed around. I'm not sure if everybody got to see it. The tricky thing was, as Tom mentioned when he was talking about it, was we were trying to get it to retract, either using rubber bands just to get it to naturally return to that state, or using a vacuum. And one of the biggest problems with vacuuming it was we weren't able to reliably seal it. And so if we vacuumed the thing, then we had fluid flowing in the opposite, or leaking in and flowing up towards our pressure sensors, which is a big no-no. So that was something that we sort of shied away from. But I think the prong is really a promising design, because the main issue that we had with resisting the flow for our circular balloon design was that the cross-sectional radius of it was big relative to the flow that's coming in, whereas the prong, it had sort of a pointed tip, and so that provides a good shearing force on the fluid and allows it to sort of pass around and go by those prongs. So in a sense, yeah, it may not be able to provide as much anchoring force, but I would speculate that the amount of force that it's facing from the fluid flow would be less. So that's something that's worth looking into. Yeah, again, the main issues that we faced were resisting fluid flow. We scaled down the flow of our pump a lot from what the actual systolic flow rate would be in the heart. And even that, it was, as soon as we introduced a little bit of flow, the thing just would go flying back into the tub. And so, yeah, there's sort of some design iteration to do there. That was the biggest issue, I would say. And the other one is when we're doing this pneumatic actuation, you may have been able to see it in the video in the wet environment that Neeraj showed earlier, but we're getting a lot of air bubbles that just from leaks, it's really difficult to seal these things with the manufacturing means that are available to us. And so, yeah, obviously you can't pump air bubbles into somebody's aorta, otherwise that's going to cause way more issues than what you're trying to fix. So, yeah. And yeah, so the future work, again, I've already hit on some of these points, but it would be to iterate our design and try to reduce that cross-sectional area, because I think that's really directly proportional to the challenge that we're facing in terms of resisting the fluid flow. Improve maybe the anterior tip design to provide that sort of shearing force. Again, that's what our prong design had, was sort of a pointed tip, as opposed to the radial balloon design, which was just sort of a flat thing and doesn't provide much shearing on the water or fluid, whatever it might be. And then, yeah, experiment with alternate actuation. We really it was sort of outside our scope. We did some early stage experimental trials with SMAs, but ultimately we had to go with our final design with the balloon design just for ease of manufacturing. For the test apparatus, it could be improved by simulating more of like a pumping environment. We just have it set up so it's capable of doing one constant flow, but if you actually wanted like a realistic heart-like environment, then it would be able to oscillate between the systolic and diastolic rates, and so maybe include some sort of control with that. And then, yeah, modify the design to actually be able to include like a camera or a stent or a little robotic arm if you're delivering like a patch within the aorta, and so that would just be, that's sort of an auxiliary objective of the project that, yeah, we might need to compensate our design for including one of these things so you can actually do something medically with the device. And then lastly, yeah, like you saw, our device is tethered right now, which with the pneumatic design is sort of unavoidable. You'd have to be very, very clever to have an untethered pneumatically actuated thing. And so, yeah, but maybe that's possible with SMAs, or if we sort of rethink our design, that might be possible. But ultimately, we would like to have an untethered device, but yeah, that's just sort of out on the horizon. And so that concludes it.
Okay, let's get to questions in a second. Before we do, I just wanted to introduce our guests who have come. So Nikki is with Autodesk, and maybe you can introduce some of the other people who...
We brought some other people that were visiting from the Bauhaus in Germany.
Okay.
Sort of an incredibly long, fabled design college and things that was the new iteration.
I'm in the study abroad office here at UCSD.
Okay. And this is Lisa from Autodesk's Office of the CTO, and I'm a fellow at the Office of the CTO at Autodesk, and working with the educational experiences team to look at the future of learning. So we've been spending the day here exploring.
Great.
And then
I'm Stephen Dow. I'm a professor actually in cognitive science and work in the design lab, so
Okay.
very, very cool to see this stuff.
So thanks a lot for coming, and just to give you guys a brief summary, so these are our final presentations. Yeah, you just hit stop there.
We may not be able to stay for too long, but we've got to catch a flight, but we heard it was happening and we thought it was catching it.
I'm very glad that you're able to make it. And so these groups are tackling a variety of topics, all sent around the central theme of soft robotics and the idea of actuating soft structures and soft materials. And this group, as you probably caught on, is looking at a small soft robot that can navigate through sort of the aorta to the inside of the body. So yeah, I think that's about it. Whenever you guys have to go, that's fine. We hope to have some demos, but we have 3 more presentations before then, and I totally understand if you run out of time and have to go.
Yeah, we're just happy to be here. We got a chance to walk into Mike's lab a few months ago, and it was pretty exciting to see. And I would say from our standpoint, Autodesk just making interesting tools to help people make crazy interesting things. We almost have nothing that helps with soft robotics. I mean, you might have noticed that. We have very traditional CAD tools. We might have tools that James Cameron might use, to do Avatar that has lots of soft stuff, but they're actually not mechanical. So we've got some interesting ways of simulating things, but nothing really for this whole, what I think is a whole new discipline and a whole space, which is really compliance and control and all that stuff that you guys are working on. So we're kind of excited to see, because you're on the bleeding edge, I think, a little bit of this, what's happening. It's exciting.
Cool. So thanks a lot. So with that, let's have a few questions for our presenters here.
Yeah, you'd like an honorary first question. First of all, really good job. We started, actually, since Stephen's here, I'll say this loud. We started with, like I said, with a human-centered design approach here. And one of the things we talked about was starting with a sort of a first do no harm approach and saying that the considerations are that it has to touch the sides without destroying the tissue, and it has to pass along a fluid gradient and without turning into a sail. And I think you thought really clearly about the protection side. And I know we thought about the sail side, meaning it can go against it's got to pass fluid, and it's got to do it in a relatively linear way, because any nonlinear flow of blood leads to clotting on its own. If we'd sort of really stuck to that constraint and said, absolutely, the first thing we have to do is we have to stick something into the aorta that flow can go through. Might we have come up with, or just thinking that through now, would we think about this a little different? Is there a way, I mean, I didn't come up with it, I don't know how to do this, but the inchworm has its issues unless it's counterpulsing of it, it occludes flow, and I think you actually probably got to a really good idea, which is some sort of a ring that passes flow. But is there another way to think about this, or is there, how would you just make the rings sort of as fine as possible and this part as thin as possible and kind of hope, or is there another way to go around this?
That's what we were hoping with the prong design. So you have something thin, tube-like at the center. It could even be thinner than this. You have thin arms or prongs that are reaching and latching or anchoring to the walls.
And the real trick is you're going into the femoral artery, which is relatively small compared to the aorta. So you got to go from small to relatively big.
Yeah, if we really truly take a hard look at it and really go back to the drawing board and iterating our design, is the inchworm concept even the best way of doing it? And so, even the prong anchor design still uses the inchworm concept to move, but yeah, maybe there's something that we haven't thought of. Maybe with SMAs, that's something that I'd really like to experiment more with, but that doesn't even use that sort of inching center segment, and that you'd be able to avoid sort of this connection. That was the trickiest part, was connecting the center segment to the anchors without, being able to, flow around it. So, yeah, I think, you raise a good point.
This was, I think, a really hard problem that we didn't expect to solve at this time. I think you did an amazing job just getting something that kind of moved through the tube in the way we wanted to. But I was just wondering if we just, if we'd started on the drawing board, might we have erased some things? Like, I guess my understanding of SMAs is, I don't know how you really deal with shielding. You can't boil blood, right? 90C inside your, so my only real question is maybe the way we approach this from the very start on the whiteboard, just the first, because eventually you got to do something and test it. Great, right? But maybe if we'd spent a little more time on the whiteboard, really saying, look, these are two design constraints we just can't ignore. And let's make sure even conceptually that these are, and maybe add in don't boil blood. But, and I guess kind of to Stephen's here, I mean, maybe a little more design thinking. We might have changed how we, sometimes it's good to just hop into stuff, which we did a little bit. But is there, maybe for the whole class, is there a different process we might have used to sort of come to think it through differently?
Sure, good feedback.
I have an idea though, like even with your inch worm tiny feet. And I don't know, maybe someone else who knows about SMAs can answer it, but if you had your SMA in a ring and you fired it up, you could contract it that way. And then you could push that forward and then as it expanded, you have to wall.
Yeah, it would take some thinking.
Yeah.
Good idea.
So I really like your prong design because it adapts to different diameters. Did you consider using the blood as a propulsion fluid like a squid would use? And actually inflate a bladder that shoots out?
But you're going, you're sailing upwind.
Yeah, I know. But you're going to have the blood that will naturally be packing into a cavity, and then if you could clamp it and inject it as a
Like
jet.
squirt it out the back.
Squirt it, and then you release your clamp, squirt, and clamp it again.
You'd have to counterpulse, but that would
Exactly.
be interesting. Can you do that and not occlude? I don't think, the real question was, and I don't really know the answer to this, how much are you allowed to occlude? Because you do occlude. I mean, you're putting stuff in the current endovascular techniques, and you get away with a bit. The trick is, those little counter pulsations, that pressure backs up and it can cause little things like strokes or tears in your artery.
Seems like it might be fun, and I don't know how much you did on this, but to look at biomimicry, what other organisms climb up inside of blood vessels today, or other internal vasculature, and then also just looking at the current state of things like thermodilution catheters and other things that people are using to deploy stents or test the pulsing strength of hearts.
So
But they tend to be actually very small. They sometimes have balloons at the end and things like that. But they tend to do that, and they also tend to use hydraulics rather than pneumatics. Pneumatics for some of this stuff, and like a cold water bolus to measure temperature differential or something like that. So it would just be fun to explore both sides. The biomimicry side, is there someone else in nature doing a trick like this?
As an infectious disease doctor, my comment is I hope not.
Every year we seem to find something fun though.
Paul, did you have a comment?
I was going to say something similar to Kurt, where just because you were saying that nonlinear flow can lead to bottlenecks, so really what you want is something that's totally streamlined. So you want your actuation to just be directly behind whatever, clamping you have.
I really like this idea of, also looking in nature for what swims upstream.
Okay, maybe one more comment.
Yeah, so I think Adriana and I went to a talk about biofilms, and they talked about this mechanism that bacteria have to go upstream. It was kind of like I don't remember the exact mechanism, but they had.
So it's like a random walk, okay, so there are one way to solve this problem people have been investigating for a while, is microswiming, right? So one way to actuate it using flagellas, and then bacteria normally have flagellas, and that's in low Reynolds number and low scale, that's the best way to actuate it, the best way to approach. However, it's time constrained, right? So the design to make something really small is really challenging and self-contained. So one way to approach that Brian Nelson is a reference, you could probably use magnetic fields, and they made a little corkscrew, and then they actuate using magnetic fields and rotate and swims. The bad news, you can't steer as much as you wish. Which for this case I think is optimum for you guys. But by going back to the biofilm thing, it is interesting because they were basically the bacteria attached to the walls, and then they reverse the flow, and the bacteria starts actually swimming against the flow. So that's what he was trying to say.
The biofilms I'm pretty familiar with. I'm not sure where the analogy works, but I'm really interested in using maybe like pulse magnetic propulsion. And that's kind of an interesting, it would be the same, you'd be doing this, right? But it would just be a little charge that's causing the actuation. That's kind of a neat.
What about a piezoelectric polymer that you can change the shape of very rapidly?
But then it comes to the battery, right?
So for one thing, I don't think it's a good idea to not have a tether. Tether's good. We probably don't want to pull this out. We don't want it to go south too fast. So if you can have a tether, it can do any of these things. It can piezo, it can magnate, it can pulse, it can put fluids. But I just think, I think the one thing that, and I'm learning this the more I spend with designers, sometimes the more you think up front, and you can't do too much. You got to stop at some point and test. Sometimes the more you think up front about the problem in front of you, the person, you come up with some different constraints, and it can be very, I think, expansive. So you go places you didn't think you'd go, but also efficient, so you don't go down potential rabbit holes. And I almost think having somebody who's a designer give a talk on design thinking before we do mechanical engineering could be more efficient, because you have a really short class. And so if you went down a rabbit hole, you know, Dr. Tolley's going to fail you. You're in trouble. But that's the whole point is, you know, you want to go down rabbit holes.
Fortunately, it's not life or death.
How many weeks do you have in this class? You know, some upfront, you know, ideation. I don't know what the term is.
So I think that's a great point to leave this discussion off on. Definitely for, you know, and also for our visitors, this is the first time we're running this class. I think this is a fantastic suggestion for next time around. Maybe I'll be in contact with some of you guys over in who do more design thinking. But a great presentation. Thanks, guys. There's chairs now. So.